Okay, so we're back for the next talk. It's a pleasure to introduce Li-Cheng Tsai from Rutgers University, who's going to talk to us about hydrodynamic large deviations for TASEP. So all yours.
Okay. Thanks the organizers for having me here, and thank you all for coming. Today I'm going to tell you about the large deviation principle for the totally asymmetric simple exclusion process. This is a joint work with Jeremy Gustav. All right, so let me, start by telling you the model. So this is simple exclusion processes which appeared in a talk yesterday. I think it was talk of Earhart's. But today I'm going to talk about just one dimension. So you have the integer lattice, and there are particles occupying the integer lattice, and every one of them perform a continuous time simple random walk with rate R jumping one step to the right and rate L jumping one step to the left. And there's the exclusion mechanism, which says that every site can hold at most one particle. So if a particle attempts to jump into a preoccupied site, the particle is being told no, and that particle has to wait for the next turn. All right. So we like to understand the large-scale behavior of such a model. So we're not, okay, there are many questions that you can ask about such a process, but in this talk, we're gonna look at large-scale behaviors. And one way to do that is you scale your integer lattice. So instead of looking at this, you kind of imagine that you zoom out. You look at it from far away. Mathematically, you scale your lattice down by a parameter 1/n, where n goes to infinity. Now, what you're going to see depends on how you scale the asymmetry. So the asymmetry is what you think it is, the difference of R to R and L. If you scale the asymmetry down to 0 appropriately with the scaling of the lattice, then what you're going to see is some parabolic behavior. So there's a parabolic scaling of the underlying process, which I'm not going to get into. And once you take n to infinity, you'll see a parabolic PD that describes the large-scale behavior of the evolution of the exclusion process. In this case, it's actually a parabolic Burgers equation. And on the other hand, if you keep the asymmetry strictly positive, you don't change it, and the appropriate scaling turns out is hyperbolic, which I'll get to in just a moment. And the kind of PD that you see describing the large-scale evolution as a fully nonlinear hyperbolic PD. In this case, it's the invincid Burgers equation. Okay. Now, in this talk, I'm going to also talk about large deviations from its typical behavior from its so-called hydrodynamic limit, which is the thing described by these PDEs, the deviation from that. And it's pretty well established in the literature at least for the weakly asymmetric simple exclusion process, that the kind of large deviation that is seen is what I call Friend-Wessel-like. It's in a sense similar to the kind of large deviation that you see in diffusions, where you have a function that controls the deviation of the underlying noise, and you kind of just plug it into the equation. You have a PDE perturbed by another given control function, which models the deviation of the noise. So that's what I call Friend-Wessel-like. And on the strongly asymmetric side, as we'll see in this talk, the deviation is very different. It's something to do with what's called Khrushchev entropy production. And what I described here on this slide, weakly asymmetric and strongly asymmetric, is sort of fairly general. It doesn't just apply to the simple exclusion processes. But for the sake of concreteness, and also because the result only applies to this model, I'm going to focus on just this model. But the idea, the distinction between the two, it goes beyond exclusion processes. Okay. All right. So in this talk, I'm actually going to talk about a special case of the strongly asymmetric exclusion process, which is totally asymmetric. So particle only jump one step to the right. They have the random clock, and they jump one step to the right. And to analyze exclusion processes, it's convenient to consider what's called the height function. So it assigns a height function whose slope is either +1 or -1. And the way it goes is whenever you see a particle, slope is 1. So this segment, you see slope 1, 1, 1, 1, 1, 1, 1. These are the segments where you see a particle underneath, and the other segments have slopes -1. Okay. And the dynamics of the particle translate into dynamics of the height function by saying that a local max can be converted into a local min at rate 1. Okay. All right. So this is our model, and we'll see what's going on. Okay. So first, let me recall from literature what's known about the hydrodynamic limits of the TASEP. Okay, so you perform a hyperbolic scaling, as I said. So you scale time by n, space by n, and also scale the height function by 1 over n. This is centering just for aesthetic reasons. And assume that initially the height function converges to something deterministic. All right, so you could have something that looks kind of funny at discrete level. I'm assuming that as n goes to infinity, this thing zoom out to a nice deterministic function f. And what is known in the literature is that the evolution of a random height function, even though it's random, it converges to something deterministic given by this Hamilton-Jacobi equation of Burgers. I know some of you in the audience is more familiar with Burgers equation. So this statement is equivalent to, if you look at the empirical density of the TASEP, which roughly speaking is the x derivative of the height function, then it converges to the Burgers equation. So these two equations are equivalent upon this derivative. Okay, so that's what's known in the literature. Now, in the next slide, I'm going to try to, in a few lines, I'm going to try to give you some heuristic idea where does this PD come from. It doesn't just come from nowhere. Okay, so one thing you could do is to try to write down the sort of equation, the discrete Langevin dynamics of the height function, which I defined to you probably 2 slides back. Okay, just try to sit down and write it. It takes some time, but take my word for that. It's not a very difficult calculation. Think about how the particle moves, one step to left and one step to right, and they are governed by some Poisson clocks. I just write it down. And you simplify the equation, take my word for that. This is what you're gonna get. Okay, so you can simplify the equation into some parts that looks like a Laplacian, some part looks like a gradient square, and some part that involves martingale. And martingale comes from the Poisson process, and you have to center it. But those are just calculations, which I won't show you, but take my word for that. And remember, we have this hyperbolic scaling, so you also have to do the scale. Okay, so here, this delta n is the scale discrete Laplacian. The nebula plus sigma minus are the scale forward and backward discrete gradient. Okay, so right off the bat, you see some sort of discrete PD. Okay, so if I'm not being very rigorous, which I'm going to do, then I can kind of, again, this is very non-rigorous. I can kind of think this as a approximation of 1 over n of the actual Laplacian, and this thing looks kind of like gradient square. And then I have some martingale. If you calculate the correlation or covariance, you'll see that looks like a noise. Okay, and because of scaling, you get 1 over 2n here and 1 over n here. So very formal. And again, this is not rigorous at all, but very formal. If let n goes to 0, n goes to infinity, this guy kind of just got killed, and this kind of just got killed. And then you have this PD here. Okay, so at a very heuristic level, this is how we see this PD arise. Now, there's one piece of thing I kind of swept under the rug, which is that for experts in the audience, they'll know that this fully nonlinear PD, the solution of this PD is not unique. Okay, so this is something we'll get to in a few moments. But because of the fully nonlinear nature of the partial differential equation, you cannot uniquely specify the solution by just saying that I solve this equation. So there's an added notion that you have to attach to a solution in order to uniquely quantify a physical solution. And one way to do that is to introduce the concept of entropy. So among all possible solutions for fixed initial condition, there's one and only one that satisfies an additional assumption that's called the entropy condition. And that way you can uniquely specify a solution. And when I stated the theorem, I implicitly assumed that this solution is the entropy solution. So how does that happen? Well, the way it happens has something to do with this vanishing viscosity, the vanishing second order term here. It is, for people who have studied the viscosity limit in Burgers equation, they'll know that even though this second order term goes to 0, it has a lasting effect of picking out the entropy solution. So it doesn't just give you an arbitrary solution of the Burgers equation. This viscosity, even though it doesn't make its way to the limiting equation, it has a lasting effect of picking out the one and only one physical solution. Okay, so this is sort of a contrast between the hyperbolic region and parabolic region. In the hyperbolic region, there's some term that just formally goes away. but they don't actually just leave. They leave some mark on the limiting behavior, just not directly. Okay, and at the level of hydrodynamic limit, you don't see the effect of the noise. Right? So noise goes to zero, and at the level of hydrodynamic limit, it's as if it doesn't do anything. But as we'll see later, that just like how this detonation viscosity picks up the right solution, quote unquote right solution, this noise would have some lasting effect in the hydrodynamic large deviations. Okay. Any questions? So far, so good. Okay, let me know if you have any questions. All right, so the next question that we're interested is to understand, sort of the atypical behavior from its hydrodynamic limit, right? With high probability, we're going to see that the height function converges to the entropy, the unique entropy solution of Burgers. What happens with, unlikely events? What kind of deviation that you could have? And to answer that question, I'm going to look at a sort of simple example. Okay, so let's say I'm starting my TASEP from what's called the step initial condition. So all particles, or all sites to the left of origin is being occupied, and every site to the right of origin is empty. Okay, and the way I define the empirical density is that whenever I have a particle, the value is 1, and whenever I have a hole, the value is -1. So the empirical density initially was like this: step function 1 on the left, -1 on the right. Now, if I try to solve Burgers equation from such initial data, the answer is well known. Okay, so it's what's called a rarefaction thing. So at any later time, if I try to solve Burgers equation from such a step initial condition, what I get is the step being connected by a linear function. Now, for people who know the theory of characteristic, which can be used to solve full hyperbolic and nonlinear hyperbolic equation, this is a characteristic. Each of the line is a trajectory in space-time where the value of u is constant. Okay, so these lines are the lines where the value of u is 1, and these lines are the lines where the value of u is -1. And in between, you see a fan that kind of models this this linear piece that's connected. So the thing just opens up. Time goes downward. So that's nice. So that's hydrodynamic limit. So let's ask ourselves, what could happen if I have some rare event? Well, one way to cause some rare event is to slow down the traffic, slow down the particle flow a few sites around the origin. I can try to artificially slow down a few of the jumps. And what's going to happen then is you're going to cause a traffic jam, which is manifested by having a jump in the density. So to the left of the origin, the density is going to be higher, and to the right of the origin, the density is going to be low. That's one way to realize an unlikely event. And you can try to solve what kind of profile you're going to get from such a thing. This is done by landing in one kind of slowdown scheme and separately in a different kind of slowdown scheme. What you're going to get is something, again, something explicit, something I'm showing you by the method of characteristic here. So that's the sort of the profile you get if you do this kind of slowdown. And surprisingly, you can plug in checks, and you'll see that such a profile here still solves exactly the same PDE. It's just that such a solution is no longer the entropy solution. Okay, so the way deviation realizes itself is that it's still solving the same PDE, but among all the solutions, it doesn't pick the physical one anymore. Pick some other solution, which is actually, without the existence of the noise, would be a non-physical solution. Okay, so here's sort of the rough idea we learned from the previous slide. The space of deviations should still be, the set of weak solutions of the same PDE of Burgers equation, but it's just that you don't necessarily have to pick the entropy solution. And what about the probability? How unlikely such an event is going to happen? Well, remember I told you how did I realize the deviation? I slow down a few sites at the origin, right? So the time span is of order n. So I slow down a few sites and the time span is of order n. So the probability is exponential minus n, order of that. Okay. So this idea has been proven at its full generality by Jensen and Varada. So they proved that up to this super exponential n probability, the empirical density of TASEP concentrate around weak solutions of Burgers. Okay, so that's really is a theorem. But how do you describe the rate function, right? I have gotten the speed of the deviation, the space of the deviation. How do I, measure how unlikely, that event is going to happen? And it has something to do with the Kirchhoff entropy production. All right, so I'm going to come up with a function which I'm going to call entropy. Okay, so this is a convex function of V, and the reason I'm coming up with such a function is that the TASEP, or actually any exclusion process, has product Bernoulli as its invariant distribution. So with that in mind, it is at least natural to look at the large deviation rate function of sums of IID Bernoulli. And if you take your textbook, you'll see that this is the rate function. So this is the rate function of sums of IID Bernoullis. I kind of took that as my entropy function. And the reason is that IID Bernoulli is invariant distribution of TASEP. And out of that, it then standard in the context of fluid dynamics to come up with what's called entropy flux. So it's defined here. And the reason that's called entropy flux is that if you pretend the solution of the Burgers equation is smooth, then you can just use chain rule to check that this quantity is true, that this thing add up to 0. Should there be a 1 minus V in the second term? Yes, my apology. So I think this should be minus. Thank you for pointing that out. Yeah, that's my typo. Thank you. All right, so the reason that this thing is called entropy flux is that if you pretend everything's smooth and you apply chain rule, then this quantity holds. So put it differently, the flux of this entropy is encoded by this J Bernoulli. Okay, but that was assuming Burgers equation, the solution U is smooth. And as we know that in general, solution to invincible Burgers equation is not smooth, and especially that's the case whenever you have shock waves. Okay, so what happens when you have shock waves? Now you can do a simple back of envelope calculation. You look at the simplest case where you have shock, where just constant. So constant on the left, constant on the right, and you have a shock like this. Well, there are two kinds of shocks. One that satisfies entropy condition. That one, the one that you see, which is typically conceived as physical one, and there's another one which goes the opposite way, which is the one that you see on the previous slide, like the one here. This is non-physical shock, okay, or non-entropy shock. You just plug in calculus. It's not a very difficult calculation. That when you have entropy shock, this quantity is negative, and when you have non-entropy shock, this quantity is positive. And remember, at least I've tried to convince you 2 slides back that the way we have deviations to non-entropic naturally should characterize how much non-entropic shock are there. And this is what Jensen Varian proposed. You look at this quantity, it's positive whenever you have non-entropic shock. So you look at this quantity, you look at its positive part, which again characterize non-entropic shocks, and you integrate over space-time. That's the rate function. All right. So what was also established in Jensen Varian is that TASEP satisfies a large deviation principal upper bound with the rate function they propose. So they have half of the theorem. Now, in order to complete this program, you have to find Mason lower bound. It has been done in Jensen, Varian, and Volinsky around some specifically construct weak solutions. And let me remind you that in order to push this Jensen Varian result to the full large deviation principle, you need to find a Mason lower bound around any weak solution, arbitrary weak solution of Burgers. And there's just one problem of that. We don't really know, what do they look like? The space of weak solution of Burgers, or a more general hyperbolic nonlinear equation, is pretty exotic. And this reason, this problem has prompted the study of properties of weak solutions. I've listed a lot of people here, and the list goes on. But still, the problem is still unsolved. We can't quite using our knowledge on weak solutions to find a Mason lower bound. There has been some other results in different models, in random PDEs, and in something called gamma convergence of the rate function. And also they have, they suffer from the same issue that we don't really know what weak solutions look like. And so there's always full upper bound and the partial lower bound. All right, so the result I'm going to tell you, present to you is a joint work with Jeremy Costel. We proved the full hydrodynamic large deviation for the TASEP. And the rate function we got is essentially the same as Jensen Varian function, except by taking limit nth along a set of specifically constructed weak solution, which we call elementary weak solutions. Okay, just quick word about this result. compared with what has been proven in Jensen-Varda, the real improvement doesn't come from lower bound, right? We might think that if I somehow close the lower bound, I can solve the problem. That's true, but that's not how we did. Instead, we actually get a sort of improved upper bound, so that actually bring the upper bound into the lower bound, not the other way. Okay. Now the method, I'm just going to say it in words. The starting point is the exact determinantal formula of the transition probability. It was a paper by Konstantin, Jeremy, and Daniel from 2016. And we use that formula to extract the finite dimensional large deviation from this formula. And we match the finite dimensional large deviation to this Jensen-Varda for special weak solution. I think I'm running over time. Sorry about that. I'll stop here.
No, I think it's fine.
Okay, but anyway, this is where I start.
Sorry, I had a problem with my microphone. You still have 5 minutes.
Yeah.
So if you, I mean, actually, no, sorry, we still have time.
Okay, we still have time.
Yeah, time. So we have until 2 for this talk. So there's 15 minutes, and
okay,
including the questions. So
okay, so let me just say a few words about the method that we have. So we take a very different starting point. The exact determinantal formula was derived by Konstantin, Jeremy, and Daniel a few years back. I'll tell you a little bit more about that on the next slides. And we try to extract the finite dimensional LDP from this formula. So it's a very different game. It's no longer trying to derive some sort of dynamical equations and using entropy method. No. It's a very different game. It's a game of analyzing exact determinants specifically. And once you've done that, if you work hard enough, you'll be able to find the finite dimensional large deviation of TASEP from that. And what you're going to do next is to try to match that finite dimensional large deviation to Kirchhoff entropy production. And there we found the elementary weak solution. And then by just taking approximation, you can prove that this gives you the full large deviation principle. Now, the proof of this is quite technical, so I'm not going to tell you all about it. I'm just going to give you some idea or taste overview about how do we extract the finite dimensional LDP from the determinant. So this is the result I told you earlier by MQR. So what you can do is to look at the TASEP height function and start from some generic initial condition, deterministic. And you ask, if I evolve the thing sometime t, and ask, what is the probability that at later time, the height function is below a given threshold AI at position xi? Okay, so that's a legit question, the probability. And as it turns out, TASEP is exactly solvable. And there's a lot of work going on into this. And one of the high point of the achievement is that this whole probability can be expressed by some explicit Fredholm determinant, where Kn is an explicit trace class operator that depends on all the parameters you think they should, time, the point that you're probing, and the initial condition. It's explicit, so that's the point. I'm not going to write it down because it's going to look very technical. Okay, now I'm going to just briefly remind you how Fredholm determinants are defined. So this is Fredholm determinants, and it's defined. The standard way to define it is to write it as an infinite series. The first term or zeroth term is 1, and the first term is the trace of this operator. And the second term is essentially a quadratic version of the trace, and cubic term is a cubic version of the trace. I'm not going to write it down, okay, but it just take my word for it. That's the definition. So how do you extract health from such expression? Well, this, in the case of one point, if you're only caring about the large deviation at a given point, this is actually pretty standard in integrable literature or in random matrix theory. It's how it goes. So I'm going to specialize into what's called the wedge initial condition, which is the step initial condition I told you earlier. I'm going to just probe at a single point, so m equal to 1, okay? And take my word for that. In this special case, as n goes to infinity, this series behaves very nicely. So the zeroth term, which is 1, is much bigger than the trace. And the trace is much bigger than the quadratic trace. And the quadratic trace is much bigger than cubic trace. So the series behaves in a nicely ordered fashion. And in order to do asymptotic analysis, in particular, in order to extract the tail, really what you need to do is to analyze the trace on, and the rest are just sub-Liouville terms. So that's nice. And this is pretty standard in the integrable literature. And the challenge is that when you look at more points, this is no longer the case. So you can do some case study, and what happens is that the terms start to cancel in a crazy way. You have terms that are very big and very positive big and very negatively big, and they start to cancel in a very undesired fashion. So the challenge in this game is really being able to recognize all that kind of cancellations and get them out of the window before you start doing asymptotic analysis. So that requires some combinatorics. And then once you've done enough of that, the remaining will behave nicely. So that's basically how we extract this finite dimensional large deviations. All right, I think that's really where I will stop. Thank you for your attention.
Let's thank Li-Cheng. And we have time for questions. So if there's any questions in the audience.
Well, may I ask a question?
Please.
Of course.
Well, the question is really very, I understand that this is the exact computation, but is there any hope now that you know the rate, you modify the rate function, so you know the rate function. Is there any way to give a softer argument which would not be depend on exact calculations and determinantal processes and stuff like that?
Right. So there's actually, it could be hope, but I can tell you something else, which probably is related to your question. There's some takeaway from this work that is not in the vein of exact solvability. So there's okay. So if you go back to Jensen Varda, they prove that there's an upper bound for around any given weak solution. So what happens, into the actual large deviation? There are two possibilities. One is that, it's just true that you have a matching lower bound around any given weak solution. There's another possibility that there's some better weak solution and some worse weak solution. However, as far as large deviation is concerned, it's always about those better weak solutions. So there are two possibilities. And what we have verified is that the second possibility is true, that we only need to engage ourselves with those nice weak solutions. And there's one thing I didn't mention, which is about the second part. And the second part, of course, comes from the first part, but it can be stated purely in terms of PDEs, nothing to do with exact solvability. So what we did, okay, so let me take the case of narrow wedge, for example. So this is narrow wedge initial condition, H0x. And the hydrodynamic at some later time looks like this, HTX. And you want to ask, if I put some points here, what's the large, what's the most likely deviation going to be? And it's pretty simple. You just connect these dots, and then it kind of touch this thing tangentially. But that doesn't fully answer the question, because it only tell me what's the most likely trajectory at terminal time. But what about in between? Okay, and this is really the second step. This is the matching step. So what we found is that if you now take this red height function and you evolve it backward in time by half-lives, the entropy solution, backward in time, then that is the thing that match the rate function. And this actually has been already observed in Jensen and Varda. So they took the 1 point case, and we show that this is true for any point, but that's for the narrow wedge. Okay, so here comes the interesting thing. What happens if you don't do narrow wedge? Well, you could consider two wedges. You have two wedge initial condition that looks like this. Okay, and you can probe finitely many points here and there. And what about the same statement? You can ask what is the most probable height function that realizes deviation, and what is the sort of in between. And the way it goes is you do the same thing separately. Ignore this and ignore that separately. and then evolve them backward by half-life, ignoring the other part, and then you take the max of the two pieces. So that's the general.
This is the effect of the first order. It's because it's first order.
Right, exactly.
First order.
Exactly. So if you write down, this is first order, and because you are doing large deviation, the second order don't compete. Exactly. Yeah.
Thank you.
No problem.
Oh, Li-Cheng, I have a question. It's maybe a little bit silly. It's about the Bernoulli entropy. So you because so when you look at large deviations in the parabolic case, the Bernoulli entropy doesn't appear anywhere in some sense. No, it's so the large deviation functional only depends on some numbers, no, that associated to the invariant measure, but not on the whole structure, in the sense that you can have different models that they have the same rate functions if they some moments match, no. But here, and I'm puzzled by that, because in principle, this is not the only entropy, no. That
okay, so you mentioned a result I'm not aware of. You say in the parabolic case, so that models with different invariant distribution that have the same rate function.
Yeah,
I'm not aware of this. So
yeah, it's because the large deviations functional only depends on some constants, on the diffusivity,
but also depends on the distribution of the noise, right?
Yes, but the point is that in the parabolic there is some central limit theorem happening. So at the end of the day, it only depends more or less on first and second moments of the invariant measures. And but here your entropy solution depends on everything.
Right.
So I'm puzzled by that. Okay, so
me too.
Yeah,
but I can tell you a result. So this is in physics literature. You can do is you look at the parabolic large, the KOV large deviation, and you do actually it's not only in physics, also in math. You do viscosity with them, it converges to this thing. So I was under the impression that they're consistent, but you just told me that they aren't. So sorry, I don't know.
Yeah, I mean, okay. Maybe the point is that for the Burger's equation, there is more than one possible entropy.
Right.
So this choice that you do of the entropy, of choosing the Bernoulli entropy, is not unique. You could have chosen another entropy and could have obtained a similar result. But of course, given the model that you are looking at, this particular one is the most natural one.
Right. Yeah. Okay.
Okay, I'm puzzled by that, and I don't know if you have any comment on that. That it seems that there is something there that.
Okay, thank you for letting me know. I wasn't aware of the thing you described.
Okay.
Are you asking? Sorry, I did not quite get. Are you asking if you take different entropy flux pair, then you can still extract the same large deviations rate function, or what?
Yeah, I mean, principle it should be, no, because.
I mean, yes. So what you are saying, there are many entropy flux pairs, and in principle, you could have taken the different one and define a similar quantity. Yeah. Whether you would get the same, I mean, you should get the same large deviations rate function, maybe.
Yeah.
Was that the question? I didn't.
No, it was not a question. I mean, I was wondering whether, I mean, it was more like a comment whether Li-Cheng had more intuition about that, no?
I had the wrong intuition, anyway.
Okay.
Okay, I have a very, very short, okay, hopefully a very short question because we're out of time, but maybe a bit technical. But so the initial data here is not really very restricted. And I'm asking just because these formulas only work for when you have a first
So
part.
the way we did it is we use a finite union of wedges. So something like this. And once you've done this, you can approximate general initial data by something like this.
And somehow you can paste this with the, I mean, the limit goes through, you have to prove some extra.
So
estimates.
as far as determinant is concerned, we only work with this. And the approximation is using just analysis.
Okay. Okay, thanks. Okay, so let's thank Li-Cheng again for the very nice talk. And